I know where there's some, right here in the hall, clerk.
No, Molly, not in there. I have enough.
Hello and welcome back. Part 6 of the Hickok 209A monster meter. In the last video, we got the meter movement itself functioning, I believe, and it's time to move on to the rest of the chassis. And let's start by doing what I would normally do in a radio, which is finding out whether the transformer this has a power transformer, whether the transformer itself is working. So let's take a look at the power supply in this piece of gear, and it's right here. AC comes in, wall socket, mains, on-off power switch. Here's a capacitor to reduce noise. That'll have to be replaced, so that one's got to be replaced. The primary is here. We can test for the DC resistance on the primary, and then we'll go over to the secondary. And this power supply feeds a 6x5 dual diode rectifier in full wave configuration. So it's a full wave rectifier. More efficient, less smoothing required. So it's got a center tapped secondary, 175 volts on one side, 175 volts AC on the other side. It also has a winding for 6.3 volts for filaments and light bulbs and things like that as well. The output of the rectification, well, there's a clue here how this works, and that is this capacitor right here is keeping the center tap, which is the neutral, if you will. Everything revolves around the center tap on the secondary of the power transformer. So this C9 here kind of floats the center tap above ground, allowing the designers to put these resistors in here and tie this point to chassis ground. So ground is there and ground is there, and that allows this power supply to generate both minus 100 volts DC here and plus 100 volts DC here. And having those two voltages is what kind of drives this dual triode operation here. This is the working part of this meter. This is the Wheatstone bridge, the active Wheatstone bridge that drives the meter itself. But we'll get to that later. So we have a power supply here with single primary, of course, center tap secondaries. We can check the DC resistance on those and the DC resistance on the 6.3 volt winding as well for the heaters for the 4 tubes here. 5 tubes if you include the AC probe. What else is to say? Nothing. Let's check this. Let's see if we have some resistance here. Now the power comes in through this cord, through the front panel here, over here to a binding post, and then back to this switch. This is the on-off switch. One side of it usually goes to the on-off switch. It's switched back, and right here is the 6x5 rectifier tube, and you can see the lines coming from the power transformer onto that tube here. We should be able to check our primary by connecting an ohmmeter to one lead of the power plug, and then to this output side of the on-off switch, which will bypass the on-off switch in case it's funky. So let's see if we can do that. I don't know which side of this goes to which, but we'll find out here in a second. Make sure our meter is metering. It is. Let's see if this is connected to the power switch. The power switch has a connector pin here and a connector pin here. So let's see if we can pick up this plug on either side. And there it is. So this plug is connected here. And it's open on that side. Let's see if it's switched on. There, it's switched on. Now it should be coming through to this side. Put this back. And it is. Whoops. Was there for a second. And it is. So our power switch is working. So we know we've got well, actually, since we know our power switch is working, we can just leave that there. We should be able to connect this here and see what the DC resistance is on our primary winding. Okay, I had to knock some oxidation off there. It wasn't reading very consistently. So, meter across the two leads, our power switch is on. Turn this to ohms. 25.5, 25.4, 25.4. So that's about right. 25 ohms for the primary of the power transformer. That looks good. I'll make a note of that in the schematic. Now we can check right here across the both ends of the center tapped secondary transformer by going to pin 3 and 5 of the rectifier tube. So all the tubes are out of here, by the way. I took them all out and tested them. They're all fine. So here's pin 1, 2, 3. And pin 5. And we've got about 310 ohms. 330 ohms, rather. 330 ohms from here to here. Now, if I can find the filter cap, I know it's right here. Well, the negative side of the filter cap is going to this line, the center tap of the secondary. So from there to pin 5 and to pin 3 should tell us whether we've got pretty balanced DC resistance between the two halves of the secondary. So let's see, I'll leave that on pin 3 of the 6x5, and I would guess this maybe. Yeah, that'll be it. That's not an unexpected resistance, so 161 ohms from here, the center tap, to pin 3. So we got 161 ohms here. I'll make note of that. We should have about that same amount when we go to pin 5, which is here. 169.6. So we've got 169.6, 161 there. They are close enough. So our power transformer appears to be in good shape. And that's important for us to know. That means we could, if I was of a mind, power this up. But I'm not of a mind right now. I want to take care of this mess first. I just wanted to make sure that it didn't need to start worrying about what to do with a power or for a power transformer for this. I don't need to worry about what to do for a power transformer for this. This one appears to be just fine. This meter out of the way. So we can kind of summarize what needs to be done to the chassis here in pretty short order. As I said, I've tested the tubes. We have a bunch of, not a bunch, quite a few of these waxy paper caps. There's one there, one here, some up in there. By the way, if you watch the first episodes, you'll recognize this wire. These are precision wound resistors wound using manganese wire. And we can go through those pretty quickly and find out whether they're open like the one that was in the meter movement itself. I suspect not. I think this was isolated. The meter movement was kind of facing the world, and whatever got splashed on this this control panel, this front panel of this meter, might have made its way into the meter movement. Not so much back here. So I'm fairly confident that this was a low moisture environment. So hopefully we won't have to do anything with these resistors, but we have some caps to replace. These turned out, I wasn't sure what these were. These turned out they're both caps. This one is swollen. I'll replace both those. That guy, there's one that looks a bit like a mica mold right here, but I'll double check and make sure it is purely a mica. Oh yeah, there's an electrolytic that goes across the meter leads here. That'll have to be replaced. And I think that's kind of it. Check all the resistors. A lot of old carbon comps in here will have drifted. The precision ones, all the resistors on this switch arrangement right here are precision resistors. I measured the resistance across this first bank here, which is about all you have to do, and they summed up within an ohm of what they should have been. So I'll do the same for those two, and we'll know whether the precision resistors are all good. Hopefully they are. As I said, they're expensive. I don't want to replace any. But first of all, this mess. Got to get this. These are the two batteries that provide voltage and current for the ohms functionality on this meter, and they've been left in there, and as you can see, they're leaking and corroding pretty badly. So I'm going to take this entire unit off. I'll desolder here and whatever's connected, if there's anything connected back in here. I'm not sure. I don't see anything. Oh yeah, there are a couple of wires. No, there's just a bridge between these two, which makes sense. And I'll pull this off and we'll start to clean the oxidation. As it turns out, the only wire that leads to the rest of the instrument is that one right there. So I can pull these batteries and then because I need to take care of the corrosion that's happened right there and right there and a little bit right there. So what do you think? I think these are retired. Going to be retired from duty. I also have some rust to take care of, or some corrosion to take care of there too. Okay. This plastic panel is held on by that bolt and that bolt right there. So I should just be able to remove these. and free it up. And there we go. I'll go put this in a bath of something. I've gathered together some capacitors. The only one I'm off by a bit is going to be the one across the meter that I just don't have. I could order one, and I might. But it's this one right here, this 15 microfarad capacitor across there. And my suspicion is that's to dampen movement. Like I said in the last video, the coiled winding of the resistor here acts as an inductor to dampen spikes in the signal coming in here. And I think this electrolytic across the meter does very much the same thing. So I've got a 12, I'll put a 12 microfarad in there. If it feels like it's too jumpy or something, after that I'll order a 15 and we'll put that in there. All the rest of them I've got the right values for. So I will go ahead and start replacing, I'll go ahead and replace capacitors, and when I get done with that we'll come back and talk about these precision resistors over here. There, the battery holders are cleaned up and replaced. At this point I have replaced all the capacitors, the waxy paper caps. I replaced the filter cap for the power supply. These guys here are micas, which I did not replace. This one, including this one, is a mica, so those aren't replaced. But all the rest of them have been replaced. I also measured all the resistors that I could in circuit. Only one was out of tolerance, and that's that one right there, which kind of surprises me. On the other hand, this meter, in terms of hard usage, isn't used hard. It's not driven like some radio circuits are. So I guess I'm not surprised that most of the resistors, all but one, are good. Speaking of resistors, these all, I mentioned this before, I think, are all manganese wire wound. So very precision resistors. I managed to measure these resistors on this switch. This is the range switch. And there are these banks of resistors that as you switch the range, you switch down through there to take away or add resistance for each of these. And there are 3 banks of them. I'll explain why in a bit. But there are a couple of resistors that kind of gave me a little pause because I can't measure them directly with my meter. And that are these 90 megohm resistors. There are 3 of them. There's one here, and one over here. So I couldn't really measure the resistance from this point to this point because I couldn't measure that 90 megohm resistor. This just says open at 90 megohms. So I had to come up with a way to make sure that the wire wound resistors, these guys and one over here, were indeed not open. And the way you do that is by measuring the current through the resistor. And the way you do that is by getting yourself a 9-volt battery some a clip, wire clip, and your meter. This meter can be adjusted down to microamps. So if you do the calculation, 90 million ohms driven by a 9-volt source will give you a current flow of 0.1 microamps, which is a very, very small amount of current. I could go to a 12-volt battery, but I don't have one on hand. I have this 9-volt, so it's a very, very small amount of current. We'll plug the probe into the current socket, and we'll switch this over to microamps. Then we'll go from, and it doesn't matter, the resistors are in circuit, but that's okay because they're going to be the shortest path for our experiment here. We'll go from, it doesn't matter which polarity, I'll go from there to this end of this resistor. There. And then the jumper connector will go from the other end of the resistor, which is here, to the battery. And that should show me 0.1 microamps. If you watch, it's flickering back and forth between 0 and 0.1. It's as small as this meter can read. We can do the same thing with this other, this one is a 90 ohm as well. We can do the same thing, or 90 megohm rather. My connections all came apart here. One end is there. The other end is there. And then we go to the battery. Did I get this right? Yes. Oh, there it is. Same thing. So it's not open. It's probably right at 90 megohms. These are probably actually precisely 90 megohms. But that's about the limit of what I can test for in my what I have on hand. I could put, as I said, I could put a higher voltage on there and get more current through it. But I've done that to the third 90 megohm, which is up under here, and they're all good as far as I can tell. So all the wire wound resistors, all the manganese wound resistors are good. Capacitors replaced, filter caps replaced. It's time to apply a little power. Still the tubes are out. The meter is still out, but we can apply some power using or turn the power supply on and make sure that we get the voltages we want. We get some output from the power supply. So we'll do that next. Okay, I moved everything out to the garage so I could bring power supply up on the Variac and Tipton device and the isolation transformer. But I thought before we did that, I would double check myself with these resistors. I've got this digital power supply here providing 30 volts. With the 90 ohms, it should provide, or 90 megohm resistor, it should provide 3 microamps, and that's what it's doing. As I change the resistor, the voltage downward, you'll see this drop to 2 microamps. So I'm confident that these resistors are fine. I'll shut that off and we'll bring up power. Get ready to test the power supply. Just to take out any variables, I took off this 1 microfarad, I think it's a microfarad, 1000 picofarad mica cap here that goes to ground from the power supply. Here's the old power switch cut off, and I've bypassed the on-off switch, which is over here. So I'm going directly into the primary of the power transformer right here. Got the Tipton devices here. It comes on about 50 volts. Dim bulb is on. Variac is all the way down, and we're ready to crank. Oh, and our voltmeter is set up across the output of the secondary right here, right across pins 3 and 5 of the 6x5. Were it in circuit, it is not. There are no tubes in this chassis. So I'll begin to bring up the voltage. We should see this start to climb almost immediately. He said, oh, Tipton device isn't on. It should, yeah, and there it goes. It starts to climb almost immediately. We're up to 65 volts output on the secondary. Tipton device just came on, 42 volts going in, 19 milliamps, which is about right. We'll run this on up. Dim bulb is not lit, so there's no big drain going on. 77 volts, 46 milliamps, 216 volts out. And that will be 175 plus 175, which is 350. So when we hit 110, 120 volts on here, we should be at 350 or so there. On up to 106, we're at 314. There's 123 volts, 347, 350 was the target. We're close enough, I think. So we know the secondary works. Now we'll switch over to make sure that our filament winding is good. And we'll do that by going across pins. What is that? 2 and 7? Where's that other 6x5? Yeah, 2 and 7 of this socket right here. 2 and 7 should be 1, 2, 3, 4, 5, 6, 7. Right there, it's an 8-pin optical. And we've got 7.5 volts AC there. So our heater voltage, or heater winding, works as well. So that's good. The next thing I'm going to do, and I'm going to do it in between videos, is I'm going to clean up, or best I can, clean up the on-off switch. I'll put this back in, I'll put this capacitor. Actually, what I'll do is replace it. I should have replaced it in the first place with a safety cap. It goes from one side of the power line to ground, and it should have been a safety cap all along. So I'll put a safety cap in there, and I will clean up all the switches and everything. And then the next time I come back on the next episode, we'll have all the tubes in and the meter back in. I will also clean up the front panel and make it a little bit more presentable. But everything should be back together for the next video, and we can see if it all works. See you next time.
makers of Johnson's Wax.